Welcome to the first lecture in our chemical engineering design series. My name is Lunghile. Before we go into the first module of our lecture series, I'd like to give a brief overview in terms of what this design series is aimed at. I will be designing an ethylene production plant from scratch to the end as if I am designing it for real industry. Yes, it will be simplified. It will mainly cover conceptual design and a bit of detailed design. However, the aim is to create a real life setting that will help my students, especially those who are in institutions like UNISA, where they have little access to their lecturers, where it's done mainly online. So designing the plant will give me an opportunity to go through with students the applications required from their chemical engineering studies that can be used to help them in simplifying their design and getting to the solution. So welcome again, and let's get started. Okay, this is presented by Bonds Engineering. It's a chemicals division of Swakanseni. So we are doing chemical plant design. And as I said, this is going to be a complete lecture series. Let's proceed. So this module is going to cover the design basis. And the most simplistic way to explain the design basis, it's a document that fixes your design parameters. My name is Lunghile. I was educated at UJ, B-Tech Chemical Engineering. I started chemical engineering M-Tech, never completed, and ended up focusing on industry and business. So now I'm back to help other students at least finish their B-Tech degree so that you can either go industrially or go the academic route. There is my bio. This presentation will be made available so that you can go through it and check where I'm from, why I'm passionate about tutoring, and the qualifications that make me suited to be your tutor. Okay, let's get started. So what can you look forward to in this design series? Well, the first thing we are going to look at what is the design basis, right? What makes the design basis important? Who prepares the design basis? And who is the design basis meant for, right? Who is it meant for? Why do we need this document, right? And what makes it so important? Layout and content, right? What goes into the design basis? This is something that I've seen that most students struggle with because this is a technical document, and you'll find that students tend to not know how complex it should be or how simple it should be. Sometimes a document looks, a requirement, a design requirement sounds complicated, but you'll find that once you get started, once you have the right directive, it becomes easier, right? Who decides what goes into the design basis? Is it me, the design engineer? Is it the client? Who actually decides what is important and what is not important for the design basis? And then what formats are acceptable for a professional design basis? Linked to the overall design. So how does the design basis compare with other plant deliverables? For example, is it the same document as a process description? Is it the same document as a control philosophy? These are the answers that we need to get to. Is there a link with all the other documents required in the plant design? All right, let's get started. What is a design basis? Definition: it is a document that fixes the constraints of the design project, right? What do we mean by fixes the constraints? So when you're designing a plant, you're going to have certain limitations, right? It's going to be space that you are given. Sometimes you might find that you have an area restriction, which is in terms of square footage that you have. Sometimes you might have a restriction in terms of the total height that you have for the plant. Other restrictions can be the availability of raw materials, but we're going to go into those details, right? So here are some of those examples you can consider, right? Capacity, as I said, right? How big is this plant? That is a constraint. If you are required to produce 100 kgs per hour of a certain product, it's a constraint that will need to go into your design basis. It forms the basis of the design, because at the end of the day, you are trying to answer your client's question is, can you design a plant for me that produces 100 kg per hour capacity, right? Operating hours per year. Now, to reach that capacity, you need to do it within a certain time period in a year, right? So usually when we define your production, your total production required, your TPP, what we usually do is we look at it in terms of the total time required a year. That's why when they give you a target, they'll tell you that this year we must produce 100,000 tons, right? And in order to meet that target, you need to check how many operating hours do you have available, so that you can design for the fact that you're not going to have your plant operational during maintenance and so forth. Apportionment of plant into units, right? Are you going to have different units in the plant, or before the different units, as in like your product preparation, your reaction section, your product separation section? There's also the way you're going to implement the plant. Are you going to start modular? So start with a small section that will produce your initial raw materials. If you have to convert raw materials into a secondary raw material, are you going to start with the utility section? Things like that. Layout and space. Again, I mentioned this before. What are your height restrictions? What are your square meterage restrictions? Consumption figures. So your target for the day is especially on raw materials or utilities, right? If we're saying we're going to cap the electricity usage to this much per day, we're going to cap the steam usage to this much per day to make the plant profitable. Target quality, again, with capacity goes quality, right? Not only are you given how much you need to produce, the quality that you want, that will affect your design. So again, fixing the constraints. Availability and cost of raw materials. That one is quite straightforward. Obviously, when you are doing your feasibility, you want to make your plant profitable. So are your raw materials available nearby, and what is the cost? Utility considerations, we mentioned that when we looked at consumption figures. Importance. The design basis removes the need to make and avoid decisions, discretionary decisions, as much as possible. So as a design engineer, you might be tempted, like where you come across a problem that is difficult to solve in maybe one of your equipment designs, right? You have no idea the height your equipment should be, right? So if your client, or in the construction, in the preparation of the design basis, you had discussed that for all our equipment we want a length over diameter not to be above a certain amount, then you as an engineer have something that you're working with, so you're not using your own discretion. So the minimum and maximum conditions of utilities are set so that the engineer can choose design cases with the most favorable outcomes. So the fact is, your utilities, your resources, they are set in such a way that you as a design engineer can choose design cases with the most favorable outcomes. Constraints for constructions are also given considerations. So space, again, allowable tube length and shell diameters, as I was saying. L/D, allowable for vessels, right? Length over diameter, that is allowable for vessels. Engineering standards for design of pressure vessels, right? Thus, the engineer works within a set layer of boundaries set by the constraints, thus removing the need for what? Discretionary decision making. Hence the importance of the design basis. What is a design basis? Again, we're continuing with that subtopic. Who prepares the design basis? So the engineering team designing the plant is responsible for drafting and keeping the design basis up to date. However, in my experience, as you'll see in my bio, I have worked for a design company before. The client will prepare, along with one of the principals from the engineering firm, a document which details the following: what the client wants, specifics like product quality and quantity, site considerations, available utilities, local and national government regulations, key considerations. The design team will then translate this information into a design basis. Who is the design basis meant for? right? For the design team, the design basis acts as a guiding document from which the engineer can refer for data like utility availability, temperatures, and pressures. Again, we go back to that non-discretionary design that we're talking about, where now you are guided by actual resources and utilities that are available. They can also use the document to constantly check if they are within the scope. For the client, the design basis keeps them up to date with any changes that had to be made to meet the design requirements. Any changes should be updated on the design document and communicated to the client as soon as possible. What is a design basis? Continuation. The design basis can also define a philosophy of backups for critical purposes. For example, backup pumps. It can also lay the foundation for preventative maintenance strategy. Like, how are you going to have minor shutdowns 3 times a year and then your major shutdown once a year, things like that. Design basis is continuously updated until the engineering project is completed. All right. So let's have a small discussion. I know I'll be asking the question and answering myself, but when you're going through this presentation, please take time to look at this question. What considerations would have been cited in the design basis for a bank scale pilot facility as pictured above? So I'm only going to give one answer, and I hope those who are watching will use my directive to give more answers, because there's a lot of answers that can be given for that question. So the first consideration that I would put in here is space, right? So how will space affect my reactor? How will space affect the cooling of my reactor? So that's the first thing I would look at, because if, for example, if I'm working with an exothermic reactor, I know I'll be producing a lot of heat. So with the space requirements, now I can determine how big a reactor I can create, which can match a heat exchanger that can fit into this kind of setup, right? Think of other questions. I would really appreciate feedback. I will leave the comment section open where in whichever platform I post this video. I would really love your feedback just to see if you are getting a hang of where we're going with this presentation. All right. Here's a code that I liked very much from Sinot and Taula, your design textbook. Starting with a vaguely defined problem, a client's need, experimental results. Chemical engineers are able to develop an understanding of the key physics relevant to the problem, right? And from there, they're able to create something that is profitable, something that can produce and that is sustainable. Next, we're going to look at layout and content. What goes into the design basis? Again, who decides what goes into the design basis? What formats are acceptable for a design basis? Okay, let's get started. Layout and content. Is there a set in stone format that one should follow, right? This is a critical question. Like, again, there's a lot of, unfortunately, when you're still a young engineer starting out, you will have a lot of uncertainty in terms of how to start your work and the direction you should take, the format you should be using. So you need some kind of guidance in terms of how to make those decisions in terms of formats and all of that. So this will depend on the arrangement you have with the client. In this case, your client is your lecturer. However, in the case where you have the creative freedom, what is important is ensuring that all the key data required is well presented and presented professionally. So the following link is from your design textbook by Sinot and Taula. If you click on the link, it will take you to templates. There are other examples like for your pump data sheets and so forth. Please, these are very useful templates. Look at them and use them in your design. Again, depending on the creative freedom you have, it is worth remembering that these templates are quite old. So do consider spicing it up, but keep it professional. Who decides what goes into the design basis? As discussed above, there are templates that can guide the design engineer to decide what they should include in the design basis. So it is a collaborative effort between the engineering house and the client. Client provides critical data like availability of utilities and raw materials, product quality required, etc. client/design house gathers meteorological data, geographic data. However, at the end of the day, the design basis with approval from the client will be used by the design engineer as a guiding document. Hence, the design engineer will decide most of what goes into the design basis. In business, it would be comparable to a business plan, which if used correctly, guides the business in their day-to-day planning and execution. Layout and content. What goes into the design basis document? This question will be answered in the form of a table of contents based, again, on one of those templates that I found as per the link provided by Sinot and Towler. Table of contents. So general information. So give basic client information, the plant location, and contact information. Measurement system. It is important to specify what system of measurements will be used in the design, especially if preparing the design for an international client. If it should be the client, it should be easy for the client, right, to know what units you're using. So, for example, if you're using metric units or empirical units, this is particularly useful when ordering equipment, as the client will know to convert sizes or capacities to the right units before ordering. Scope of work. Give a summary of what is required. You can include some background information, including uses of the chemicals required. Depending on the complexity required, you can lay out a basic action plan that will be followed in the execution of the design. For example, simulation, manual mass balances, bench scale pilot tests, laboratory analysis. So you'll be giving examples of the things that you'll be doing in order to achieve the design. Will you be doing laboratory analysis? If you are, specify that part of the information gathering that we're going to use for this design is laboratory analysis. Are you going to have a bench scale pilot plant? Mention it. Are you going to have mass balances? Mention it. Table of contents continued. So, design assumptions and constraints. This will be the most updated section in your design basis. As I said before, your design basis is a live document, right? It will list all the information given in the design problem, like operating hours, optimal feed, molar ratios, process limitations, like approach temperatures, quality requirements, emission limitations, and many more. Any new assumptions that will be made by the design engineer during the project must be stipulated here. Let's just say you decide to have a recycle stream, right? And as part of that recycle stream, you're going to have a purge. Now, the purge, you're going to decide how much goes back into the process, how much goes to the incinerator or wherever you're going to take your waste gas or waste liquid or whatever, right? So one of the assumptions that you need to specify and which need to now be updated in the design basis is the ratio that you're going to use for that split, right? Numbering system. This section gives a summary of the numbering system and nomenclature that will be used in the design. It is important to stick to the symbols and codes that you select so that you minimize confusion for the reader. When they see a pump, it should always be, it should always start with the letter P in its code. Products. Give a list of the products to be produced, the quantity and the quality. Can be in tabulated form depending on the number of products. Raw materials. Give a list of the raw materials used, the quantity and the quality. This can be in tabulated form depending on the number of products. Information like quantity can only be finalized after the material balance is completed. Again, your design is live. So in the beginning, you're only going to have a list of your raw materials, but at the end, once you've done the design, once you've done the material balance, once you've looked at the costing and updated your material balance to fit the costing, what will then happen is you will then have a final number of the raw materials you're going to use. Therefore, you can update the design basis in finality. Okay, we continue with table of contents. Site information. So list meteorological data, geographic data that may affect the design. So for example, a place with low ambient temperature of 30 degrees will mean your cooling water may not be available at the conventional 25 degrees. Also, on very hot days, the temperature of the cooling water may affect the operation of cooling towers. Let's just say that ambient temperature goes up to 45 degrees, right? Because usually your cooling water, right? What usually happens is it does not go through cooling, right? So it does not go through cooling treatment. So as it leaves your cooling tower, it is recycled back into the system. So if it so happens that your ambient temperature is high, your feed cooling water will be at a very high temperature, right? And this means that you're going to have a problem. Utilities and raw material information. This is simply a list of the utilities and raw materials available along with prices. And then another code that I like, so repeatable occurrences such as the reaction between hydrogen and nitrogen to form ammonia birthed what is today still one of the largest industrial processes, right? The Haber process. Repeatable is equals to predictable, which is equals to scalability. This is something that I'd like you to be thinking about, not just when you're doing a design, but in your workplace, right? You should always be thinking about this, that repeatable process lead to predictability, which lead to scalability. So when you're working, right, look at your process, look at it. Is it repeatable? If yes, you should be able to predict what's going to happen next. And this is something that's going to differentiate you as an engineer from others. The fact that you can look at the process, if by the time you get to that company or since you've been working there, there is no prediction in terms of what will happen next in your process, use the skills you learn in this design course to design, to come up with those predictions that will help the company better. So this course is not only aimed at you passing your design course, it's also aimed at trying to give you the skills that can help you better yourself in your workplace. Finally, we're going to look at the link to the overall design. Comparison to other design deliverables. So the design basis, as mentioned before, can be seen as a guiding document. It is not an executive summary and it is not a process description, right? It summarizes data and inputs that were used in the design and lists all the process assumptions made. Is there a link with all the other design documents? Yes, given that the design basis forms a central philosophy, right? No, I didn't say control philosophy. I said central philosophy on how the design will be formulated. Each stage of the design should be in line with the design basis set in the formulation of the design. So with the basis set in the formulation of the design basis. In summary, the design basis sets the stage for the design project. The design engineer should take advantage to use the design basis properly to communicate properly communicate what is in store for the reader. And a nice quote by Michael Kepler. This is a very nice design book to read. An engineering project is a huge and complex task for An engineering project is a huge and complex task for usually several hundred people. Coming from the university and just having finished one's studies, one has usually no clue on what is going on beyond their own desk. In fact, the construction of a chemical plant is often compared to the erection of the pyramids in Egypt. While the weight of a chemical plant is much lower, its complexity is by far greater, and the project can usually be completed in approximately 3 years instead of 20. The target for a beginner, that's me and you, must be to become an increasingly larger cog in the machine, become increasingly more important. First, an overview of the particular phases and activities must be obtained. I'd like to thank you for giving me your time. I hope this presentation will work as an invitation for you to join me in this lecture series. I will be giving details in terms of what will go into the total lecture series. But as I said in the beginning, I will be designing the entire plant. So instead of just having a process flow diagram from one section, I'll have a process flow diagram for the entire plant. I will have a PNID for the entire plant. Equipment design, I will design each and every single equipment that will be in in the design. So this will help you as a student choose whether to do a distillation column or to do an absorption column or to do a heat exchanger and stuff like that. So I hope this will give a lot of value to you guys, and I look forward to meeting everyone who will find this lecture series in the YouTube, in the TikTok, and good luck to everyone who's starting up this year. Whoever is repeating, do not be discouraged. Most of us went through what you're going through. It is part of the learning process, and what happens is you get to open up your view of the discipline even more. Thank you very much, and yes, have a lovely day.